Welcome back to the deep dive. And honestly, looking at the calendar, the timing for this one couldn't be better. I want you to picture something with me. It is mid-November in Ontario. You are on a job site. The sky isn't just cloudy. It's that flat, oppressive, slate gray sheet that sits right on top of the scaffolding.
Oh, I know that sky. It feels like it's about 6 feet over your head.
It really does.
Yeah.
And the wind is cutting right through your Carhartts. Doesn't matter how many layers you have on, and it finds that one gap right at the back of your neck.
Oh, I know that wind. It's the kind that makes you question every life decision that led you to a trowel.
Exactly. You got that coffee you picked up at the drive-thru 20 minutes ago. It's a double-double, obviously, but it's already lukewarm.
Ugh, the worst.
The plastic lid is cold against your lip. And the mixer. The mixer is making that sluggish, grinding sound because the gear oil is starting to thicken up in the cold.
That is a sound that haunts my dreams. That chug, chug, chug before it finally catches. It is the time of year where the romance of masonry dies a little bit.
It's just a little bit. We always say the bricklayer's favorite weather is anything that isn't raining, isn't snowing, and isn't over 30 degrees.
Mm-hmm.
But let's be real, that window seems to be getting smaller and smaller every year. You get 2 weeks of perfect weather in May and 2 weeks in October, and the rest is a battle against the elements.
It really does feel that way. But functionally speaking, this is also the time of year when the schedule shifts. If you've planned your year right, the foundations are done,
Right.
the veneer work, the brick and stone on the outside is wrapping up because you don't want to be hoarding and heating scaffolding if you don't have to. So we start looking at the indoor work.
The sanctuary.
The sanctuary. And for a mason, indoor work doesn't just mean hiding from the wind. It usually means the glamour work, the high-end stuff.
Exactly. We're talking about fireplaces, the
Fireplaces.
centerpiece, the thing the homeowner is actually going to stare at for the next 30 years. It's not a retaining wall behind the shed.
No.
It's the focal point of their living room.
It is the crown jewel of the trade. But I always tell apprentices, it is also the highest stakes game we play. Think about it. If you build a partition wall and it's a little out of plumb, maybe the drywaller curses you out, maybe the baseboard guy has a bad day trying to cope a corner, but the house stands up, nobody dies.
Right. It's cosmetic, annoying, but cosmetic.
If you build a fireplace wrong, best case scenario, the house fills with smoke every time they light a match and you get sued.
And you deserve to be.
And you deserve to be. Worst case, you burn the place down. You are literally building a fire containment system inside a wooden box that people sleep in.
And nobody wants that on their resume.
Great, Arches. Shame about the arson.
No, that is not a LinkedIn endorsement you want.
So, today we are doing a deep dive specifically for the apprentices out there and, frankly, for the journeymen who might have learned bad habits from the old guys.
Oh, for sure.
The goal here is to take you from just stacking units, because the boss told you to actually understanding the anatomy and the physics of a working wood-burning system.
Yeah. We are going to be pulling heavily from the National Building Code of Canada, specifically the 2025 edition, plus some technical notes from the Brick Industry Association on Rumford designs and some standard masonry textbook guidelines.
And we really need to emphasize the physics part, because I think a lot of apprentices, and even some guys who've been laying for 20 years, treat a fireplace like it's just a box that holds fire. They think it's a static container. It isn't. It is an engine. It's an airflow engine. It consumes fuel. It manages intake. It manages exhaust, and it relies on pressure differentials.
That's a great way to put it. It's an engine. Before we get into the nuts and bolts, or I guess the bricks and mortar, we have to address the classic struggle. You know the one.
I know it all too well.
You walk into a living room. It's 12 feet wide, maybe 8-foot ceilings, and the homeowner pulls out a picture from a magazine or Pinterest.
Pinterest is the enemy of the honest mason.
It truly is. Yeah. And they show you a picture of a castle in Scotland. It's got a fireplace you could roast a whole ox in. It's 10 feet wide, 6 feet tall.
And they want that in their suburban bungalow with the vinyl siding.
You build me this?
Yeah.
And you have to be the one to tell them physically, no, that is not going to work.
It's a heartbreaking conversation, but you have to explain that a fireplace relies on a ratio, a formula. You can't just make the opening huge without making the chimney huge.
Right.
And if the chimney is huge, it pulls a massive amount of air from the room. If the room isn't big enough to supply that air, the fire just sits there and gasps for oxygen. It's like trying to put a V8 engine in a lawnmower. It won't run.
So let's unpack the design first. Because if you are on a site today, you are likely building one of two things: a standard fireplace or a Rumford. Let's start with the standard.
Yeah.
This is what most apprentices see first. It's the deep box.
Right. The conventional masonry fireplace.
Yeah.
It's essentially a deep, rectangular recess. Now, historically, this design became popular in the post-Victorian era because it's easy to build. It's square, it holds a lot of wood, it feels safe, it's a cave.
A cave. That's a good way to put it.
Yeah, literally. And that is the flaw. Because it's so deep, often 24 inches deep, the fire burns well. But where does the heat go?
Into the masonry.
Up the chimney.
It gets trapped in the box, it goes straight up the chimney. Radiant heat works like light. It travels in straight lines.
Right.
If the fire is buried deep in a square box, the side walls are just absorbing that heat or reflecting it back into the fire itself. It heats the birds on the roof, but it doesn't do much for the people sitting on the sofa.
Which brings us to the Revolution, the Rumford. Now, this isn't new tech. This goes back to the 1790s, right?
Count Rumford. Now, this is a fascinating character. His real name was Benjamin Thompson. He was born in Massachusetts, but he was a loyalist during the American Revolution, so he had to flee to Europe.
Okay.
He ended up in Bavaria, working for the elector there.
Yeah.
And he was obsessed with efficiency, just completely obsessed. He looked at the poor people in Munich who were freezing to death because wood was expensive and their fireplaces were garbage.
So he wasn't just a mason tinkering around. No, he was a physicist, a scientist. He approached it as a science. He realized that heat is radiation. He wanted to build a machine that acted like a reflector.
So for the listener trying to visualize this, what does a Rumford look like compared to that standard cave box?
The first thing you notice is the depth. A Rumford is shockingly shallow. If a standard fireplace is maybe 20 inches deep, a Rumford might be 12 or 14 inches deep for the same width.
That's a huge difference.
It feels almost too shallow. When you build one for a customer for the first time, they almost always panic. They think the logs are going to roll out onto the carpet.
It does look precarious if you aren't used to it.
It does. But then look at the height. A Rumford opening is tall. The rule of thumb is that the height is roughly equal to the width. So it's a square opening rather than a low, wide rectangle.
And the sides, the covings.
That's the key.
Yeah.
That's the magic. In a standard fireplace, the sides go straight back or taper slightly. In a Rumford, they flare out at a sharp angle, usually 135 degrees to the back wall. It's wide open.
And that's the radiant heat part, right? It's like a reflector oven.
Exactly. Think of it like a flashlight reflector or the sound shell behind an orchestra. The fire sits in this shallow box, and those angled sides bounce the heat out into the room. It doesn't trap the heat, it throws it. You can sit 15 feet away from a Rumford and feel the warmth on your face. You can't do that with a standard fireplace.
But here's the question the apprentice should be asking. If the box is shallow and the opening is tall, why doesn't smoke just spill out into the room? Logic says a shallow box should smoke.
That is where the genius comes in. The Rumford isn't just a shaped box. It relies on the throat.
The throat. Okay, this is the transition from the firebox to the smoke chamber.
Right. In a standard fireplace, the throat is usually right above the lintel, maybe a few inches up.
Yeah, pretty low.
In a Rumford, the throat is much higher, often 12 inches or 300 millimeters above the lintel, and it has a specific rounded, streamlined shape. This is pure fluid dynamics.
We're talking about the Bernoulli principle here.
We are. Rumford realized that smoke acts like a fluid. If you restrict the area through which a fluid flows, its velocity increases. That's the Venturi effect. The Rumford throat is a nozzle.
A nozzle type.
By narrowing that opening and curving it smoothly, like the wing of an airplane, he accelerates the smoke.
So it shoots the smoke up.
It creates a high-velocity jet of hot air. That jet shoots up into the smoke chamber and creates a strong draft that overcomes the tendency of the smoke to wander out into the room.
I see.
It's a laminar flow, smooth, fast, organized. A standard fireplace relies on volume. A Rumford relies on velocity.
It's the difference between a lazy river and a fire hose.
Precisely. And that's why you can have that tall, elegant opening. The velocity of the draft acts like an invisible curtain keeping the smoke in.
Okay, so we have our design. We've convinced the homeowner to go with a Rumford because they actually want to feel the heat.
Right.
And we've explained that we aren't going to burn their house down because we understand fluid dynamics. Yeah. Now we have to build the thing. Let's talk about the anatomy of the build, starting with the hot zone, the firebox itself.
This is where the trowel meets the mud and where the physical reality of the job sets in.
The apprentice workout.
Oh, yes. The rite of passage.
Because fire bricks are heavy, they're dense, and for some reason the delivery driver always drops the pallet at the curb, never near the door.
Always.
And of course the customer has a beautiful ornamental iron gate that is exactly 1 inch too narrow for the job site forklift.
So you are hand-bombing 500 fire bricks across a muddy lawn, maybe through a side window. It's a rite of passage. If you haven't carried a ton of brick by hand, can you really call yourself a mason?
It builds character and lower back problems. But let's talk about the bricks themselves. You see guys, usually DIYers, thinking they can just use regular clay pavers or standard face brick inside a fireplace.
And that is a recipe for disaster. A very loud, messy disaster.
Why? What makes a fire brick different?
It comes down to chemistry and thermal shock. Standard face brick is made of clay or shale, fired at maybe 1,000 degrees Celsius. It's designed to shed water and look pretty, but it has moisture in it. It has a certain porosity.
And when you heat it up rapidly.
When you light a fire, the temperature can jump from 20 degrees to 600 degrees in minutes. That thermal shock causes the moisture inside a standard brick to turn to steam instantly. The pressure builds up and the brick spalls.
It explodes.
It literally pops. You'll hear it pop, and a flake of brick shoots off. Do that enough times and your wall disintegrates.
Okay, so not good.
Not good. Fire bricks or refractory units are different. They are specified under ASTM C27 or C64. They are high alumina, high silica bricks fired at extremely high temperatures. They are designed to expand and contract without falling apart. They absorb the heat rather than fighting it.
Now, there is a debate on site, or at least a choice, about how to lay them. Shiners versus stretchers.
This is the classic trade-off between cost and quality. It's the battle between the wallet and the craft.
Explain the difference for the listener who might not know the slang.
A shiner is when you lay the brick on its long, narrow edge. So the wall thickness is the thickness of the brick, about 63.5 millimeters or 2.5 inches. You cover more square footage with fewer bricks.
Okay, so it's faster and cheaper.
Right. A stretcher is laying it flat, like a standard brick wall, giving you a width of about 114 millimeters or 4.5 inches.
And the code, what does the MBC 2025 say?
The code requires a minimum thickness of 50 millimeters of the sides and back and 25 millimeters for the floor. So if you lay them as shiners at 63.5 millimeter, you are technically code compliant.
It passes inspection.
It passes inspection, but is it good?
That's the real question.
In my opinion, no. A shiner wall is thin. It heats up very fast, which is good for draft, but it lacks structural stability. If a log rolls into it hard, you can crack a shiner. It also burns out faster over decades. If you want a fireplace that lasts 100 years, you lay them as stretchers. You give the customer that extra mass. It's a stronger wall. It holds heat better. It's just...
So shiners for the spec house where the builder is squeezing every dime. Stretchers for the custom job where you want your name remembered fondly.
I would say stretchers for any job where you take pride in the longevity. But yes, economics often dictate the shiner. It uses almost half the brick.
Now let's talk about the mortar, because laying these things isn't like laying a garden wall. You don't just mix up some type N, slop it on, and tap it down.
No. If you use standard type N or S mortar, which is Portland cement and lime, you're going to have failure.
Complete failure.
The heat will calcine the cement. It literally cooks the chemical bond out of it. It turns back into dust. Eventually, the fire will eat right through the joints, and you'll be looking at the backup block.
So what's the material?
You need refractory mortar. It usually meets ASTM C199. There are two main types. You have the hydraulic setting stuff, which is like calcium aluminate cement. It sets hard like concrete.
Okay.
And you have the pre-mixed silicate stuff, often called air set or heat set. That's the more common one.
And the consistency.
This is what throws apprentices off. They are used to mortar that stands up on the trowel. Refractory mortar, especially the silicate type, comes in a pail. It has the consistency of a thick soup or a pancake batter.
A soupy batter.
Yeah.
So you can't butter the brick in the traditional way?
No, you use a technique called pick and dip.
Walk us through it.
You don't use a trowel to apply the mortar. You pick up the fire brick with your hand. You dip the edge, the side you're going to bond, into the bucket of mortar. You get a thin, even coating, and then you slam into place immediately.
And the joint thickness.
Razor thin. We are talking 116th to 316th of an inch, 1.6 to 4.8 millimeters.
That is tiny. That's barely a line.
It basically looks like brick on brick. And here is the why. The brick is the strong part. The mortar is the weak link. The mortar has a different coefficient of thermal expansion than the brick.
Right.
If you have big, fat, 10-millimeter joints, they will shrink and crack under the heat.
Yeah.
You want a monolithic ceramic liner. You want as little mortar as possible exposed to the fire.
Okay, so we have our firebox built. It's tight. The joints are thin. Now let's talk about what is behind it. Because I've seen guys, and I'm sure you have, 2-pack mortar right tight against the backup block. They fill every void solid.
That is a rookie mistake, a potentially catastrophic one.
Why? It feels like you're making it solid. More is better.
You are making a bomb. Okay, maybe not a bomb, but a slow-motion wrecking ball. When you light a fire, that fire brick liner is going to get hot, really hot. And things that get hot expand. The firebox is going to grow maybe 1/8 of an inch, maybe more.
And the backup wall, the concrete block or the house framing is cold.
Exactly. The liner expands, the house stays still. If you have mortared that liner solid to the backup wall, the liner has nowhere to go. It will push outward with that thousands of pounds of force.
And something has to give.
And it's usually the facing. You'll see cracks zigzagging up the front of your beautiful stone mantle because the firebox pushed it apart, or the firebox itself will buckle inward and crack.
So what's the rule?
You need an expansion joint. Code typically calls for about 1 inch or 25 millimeter of airspace between the back of the firebox and the backup masonry.
An airspace.
You leave it empty, or you can fill it with a compressible, non-combustible insulation, like a mineral wool or ceramic fiber.
So it acts like a cushion.
Exactly. The firebox expands, it squishes the insulation, and the structural wall stays put. The insulation gives it room to breathe. If you don't leave that gap, you are building a self-destruct mechanism.
I can just picture the phone call. My brand new fireplace is cracking in half.
I went to a job once, beautiful limestone mantle, cracked right down the center keystone. We tore it out. The mason had poured concrete solid behind the firebox. It was heartbreaking.
Let's move up the structure. We're leaving the firebox and entering the critical engineering section, the throat. We mentioned earlier that this is the valve of the system.
It is. The throat is the narrowest point in the chimney system. It regulates the flow.
And sitting right on top of that throat is the damper.
The damper. Usually a cast iron or steel door that you can open and close. Now here is a pro tip that seems obvious but gets missed constantly on site. Do not mortar the damper in solid.
Say that again for the guys in the back who are mixing mud right now.
Do not mortar the damper in solid. It is metal. Metal expands much, much more than brick when it gets hot.
A lot more.
A lot more. If you lock that metal frame into the masonry with hard cement, when you light that first big Christmas fire, the damper is going to expand.
And it's strong.
It is incredibly strong. It will lift the masonry right off the lintel. I've seen mantles lifted 1/4 inch because the damper grew and had nowhere to go. It breaks the bond.
So what's the fix? How do you install it?
You wrap the ends of the damper frame in wool. Ceramic wool or strips of fiberglass insulation. You give it a little jacket or a gasket. That way, when the metal expands, it squishes the wool instead of lifting the house. It floats.
Okay, that makes sense. It needs room to move.
It has to float.
Now, directly behind the damper is something called the smoke shelf. And I feel like this is the most controversial or misunderstood part of the fireplace.
Oh, yeah.
Some people say it's just a ledge where soot collects and catches fire. Some people say it's critical.
It does collect soot, and you do need to clean it, but that's not its primary job. Its job is to fight the cold.
Explain the physics there. Because to a layperson, a flat shelf inside a chimney seems like it would stop the smoke.
Okay, visualize the chimney. It's a big, tall, cold clay pipe sticking up into the winter air. Even when a fire is burning, you have a column of hot air going up the front side of the flue.
Right, the updraft.
But on a windy day or just a very cold day, you often have a column of cold air sinking down the back of the flue.
Cold air is heavier, so it falls.
It falls right down the chimney. It's a downdraft. Now imagine if you had a slumped back wall that went straight from the firebox to the flue like a funnel. That sinking cold air would slide right down that slope, hit the fire, and whoosh.
A puff back. Smoke in the room.
Exactly. It blows the smoke right out. The smoke shelf is a horizontal ledge located directly behind the damper. When that cold air sinks down the back of the chimney, it hits that shelf.
It stops it.
It stops it. It can't go down anymore. It hits the shelf and has to go somewhere.
It bounces.
It bounces. It hits the shelf and curls back up in a circle. It gets caught in the updraft of the hot air coming through the throat.
So it creates a roller. Little weather system in there?
Yes. It creates a rolling eddy current, a cylinder of air spinning inside the smoke chamber. That rolling action actually helps pull the smoke up. It acts as a dynamic baffle. It separates the downdraft from the updraft.
So it's active aerodynamic engineering using masonry. It's not just a shelf for dead birds and soot.
Precisely. It keeps the cold air from disrupting the fire. If you skip the shelf, you are gambling that the updraft will always be stronger than the downdraft. In Canada, in November, that is a losing bet.
Okay, above the shelf, we have the smoke chamber. This is the funnel.
Right. We are going from the wide opening of the firebox down to the relatively small opening of the flue liner. That transition area is the smoke chamber.
And you build this by corbelling the brick or block, stepping it in course by course.
Step it in, but, and this is a huge but, you cannot leave those steps exposed.
This brings us to parging.
Parging is non-negotiable. Code states the inside of the smoke chamber must be parged smooth.
Why? Smoke doesn't care about steps, does it? It's gas.
Smoke hates friction. We go back to fluid dynamics. Think of water flowing in a pipe. If the pipe is jagged and stepped, the water hits those edges and becomes turbulent. It swirls. It slows down.
Okay.
The same happens with smoke. If it hits those raw brick steps, it creates drag. It creates little eddies and whirlpools of smoke.
And slow smoke is bad smoke.
Slow smoke cools down, and cool smoke sinks. If you slow the smoke down in the chamber, it might not make it up the flue. It lingers, it cools, and it drops back into the living room. You need to coat that corbelling with mortar to create a smooth, tapered funnel. It needs to be slick.
And I know from experience, reaching up inside a smoke chamber to parge it smooth while wet mortar is falling in your faces.
It is miserable work. It is the definition of miserable.
Your arm is cramping.
Yeah.
You are twisting your body inside the firebox. You can't really see what you're doing. Gravity is fighting you.
Yeah.
Every trowel of mud you put up, half of it lands on your nose.
It is. But that is what separates the pro from the amateur. If you stick your head in a fireplace and look up with a flashlight and you see raw, corbelled brick, that mason cut a corner because he didn't want to get dirty. If you see a smooth, dark slope that looks like a funnel, that's a craftsman. That fireplace will draw.
It's the detail nobody sees, but everybody feels when the fire is lit.
Exactly. It's the hidden mark of quality.
So we followed the smoke up.
Yeah.
Now we are into the chimney and the flue, the exit strategy.
The exhaust pipe.
First off, sizing. You can't just pick a flue liner size out of a hat.
Yeah.
You can't just say, I have some 8x8 liners left over from the last job. Let's use those.
No. It is pure math. The area of the flue, the cross-section inside the liner, must be in proportion to the area of the fireplace opening.
The opening in the room.
Right. If the opening is, say, 1,000 square inches, you need a flue that can handle the volume of air that opening pulls in.
What's the ratio? What's the rule of thumb?
The standard rule of thumb is 1.10 for a taller chimney. So if the fireplace opening is 10 square feet, your flue area needs to be at least 1 square foot. For shorter chimneys, you might need a 1.8 ratio.
What happens if you get it wrong? Say the flue's too small.
If the flue's too small, it's like trying to breathe through a coffee stir while running a marathon. The smoke backs up. It physically cannot exit fast enough. It spills out the front. It's choked.
And if it's too big?
Yeah.
Because common sense might say bigger is better, more flow.
That is a dangerous trap. If the flue is huge, say a 24 by 24 flue for a small bedroom fireplace, the smoke moves too slowly.
Okay.
The column of hot air gets lost in that big, cold space. It expands, and as gas expands, it cools.
Rapid cooling.
And when smoke cools rapidly, the byproducts, the tars and resins, condense on the walls of the liner. That condensation is creosote.
Which is fuel.
It is highly flammable liquid fuel that hardens into a glaze. A sluggish flue is a dirty flue, and a dirty flue is a chimney fire waiting to happen. You want that Goldilocks zone, just big enough to handle the volume, but small enough to keep the velocity high and the smoke hot. You want the smoke to exit the top while it's still hot.
Let's talk liners. What are we putting in there?
Traditionally, clay tile liners, those orange-red rectangular or square tubes. They are heavy, they are cheap, and they work well if installed right.
Installed right meaning?
Meaning they need an airspace around them, too. You don't mortar the liner solid to the chimney block.
Same expansion rule as the firebox.
Same rule. The liner gets hot, the block stays cold.
Yeah.
If they are glued together, the liner cracks. You leave a space or you use a mesh wrap. The hot flue will expand, and if it's locked in, it has nowhere to go but to crack itself or the chimney around it.
What about stainless steel?
Stainless is great, especially for retrofits or irregular shapes.
Okay.
But you have to watch the specs. NBC 2025 references standards like a 0.3 millimeter thickness for specific stainless applications. You can't just use galvanized ductwork from Home Depot.
Galvanized gives off toxic fumes when heated, doesn't it?
Zinc poisoning. Yeah, don't do that. It has to be listed stainless steel chimney liner. It's a specific product for a specific high heat application.
Now, height. This is where I see the most arguments with architects. Architects love that low-profile look. They want the chimney to just barely peek over the roof.
And you have to tell them only if you like smoke in your bedroom. It's a physics problem, not an aesthetics problem.
What is the rule?
The 3-2-10 rule. This is the Bible of chimney heights. It's in every code book from here to California.
Break it down.
Part 1. The chimney must extend at least 3 feet, about 900 millimeters above the highest point where it passes through the roof. That's for fire safety, mostly, so sparks don't land right on the shingles.
Okay, 3 feet up. Simple.
Part 2 is the tricky one. It must be at least 2 feet higher than any part of the building within 10 feet horizontally.
So if the peak of the roof is 8 feet away?
Your chimney has to be 2 feet taller than that peak, even if the chimney itself is way down the slope of the roof.
Why? Why does the peak 10 feet away matter?
Wind pressure zones. When wind hits a house, it flows up the roof. As it goes over the peak, it tumbles. It creates a high-pressure zone on the windward side and a low-pressure turbulence zone on the leeward side. If your chimney ends in that turbulent zone, the wind will literally push the smoke back down the pipe.
It caps the chimney with pressure.
Exactly. You need to get the top of the chimney up into the clean air stream, the laminar flow of the wind, so the wind actually helps pull the smoke out. It creates suction across the top. It's the Bernoulli principle again.
So when the architect complains that the tall chimney ruins his horizontal lines, you just say,
I can't change the wind, buddy. Take it up with physics.
let's move to safety. We mentioned burning the house down earlier. Let's avoid that. Clearances.
This is the stuff the building inspector is measuring with a tape measure. You cannot have combustible materials touching the masonry of a fireplace.
Combustible means wood framing, studs, joists, plywood, anything that can burn.
Right. And people forget that masonry transfers heat. It's a thermal bridge. It takes a while, but eventually that heat travels through the brick.
What's the rule for interior clearance?
Generally, you need 100 millimeters or 4 inches of clearance from the back of the firebox to any interior framing.
That's a lot of space. That's a 2x4 on the flat plus a bit.
It is, and here is why. If a 2x4 is touching the back of the firebox, after 6 hours of a roaring fire, that wood gets hot. Maybe not hot enough to burn today.
Right.
But over years, repeated heating causes a process called pyrolysis.
Pyrolysis.
It's the chemical degradation of wood by heat. It lowers the ignition point of the wood. A piece of wood that normally burns at 400 degrees might eventually catch fire at 200 degrees if it's been baked for 10 years.
Wow.
Then one day, whoosh, wall fire, and you'll never see it coming.
That is terrifying. What about exterior walls?
If the fireplace is on an outside wall, the clearance drops to 50 millimeters or 2 inches, but you still need that gap.
And the hearth extension. The floor protection.
You need a non-combustible surface extending in front of the opening. NBC says 400 millimeters, about 16 inches in front, and 200 millimeters, about 8 inches to the sides.
Because sparks don't just land, they bounce.
They pop. Softwood hemlock, spruce, it contains resin pockets. When those pockets boil, they explode. It can shoot a burning ember 3 feet. You don't want that landing on the hardwood floor or the shag carpet.
And wall thickness. You can't just put a liner against a stud wall.
No. The total thickness of the firebox wall, plus the backup masonry, needs to be at least 190 millimeters, about 8 inches of solid masonry. That provides the thermal mass to absorb the heat safely.
Okay, let's get into troubleshooting. Because sometimes you build it right, or you think you built it right, and it still doesn't work.
The dreaded callback, it smokes.
The tight house problem. This is a modern issue.
It is. In the old days, houses were leaky. Windows rattled, doors had gaps, the basement was drafty. There was plenty of air coming in to replace the air. The fire sucked up the chimney.
A fireplace consumes a lot of air.
A roaring open fire can suck 200 to 600 cubic feet per minute, CFM of air out of the house.
Yeah.
That is a massive vacuum.
But modern houses are wrapped in Tyvek, sealed with spray foam, triple pane windows. They are submarines.
They are airtight. So when you light a fire, the fireplace tries to pull air, but the house is sealed. It creates negative pressure. The house becomes a vacuum chamber. So where does it get the air?
It fights for it.
It fights the path of least resistance. It starts pulling air down the furnace flue or the water heater vent, or it fights the bathroom fan. If you have the dryer running and the range hood on, the fireplace loses that fight.
And if the fireplace loses?
The flow reverses. Smoke pours into the room because the house is trying to equalize pressure by sucking air down the chimney.
What's the fix?
You have to provide a dedicated source of air, a combustion air intake, or a fresh air kit. It's basically a 4-inch insulated duct that goes from the outside of the house directly into the firebox or the immediate area.
So the fire breathes outside air, not room air.
Correct. The NBC requires this now for most solid fuel appliances. You cannot rely on infiltration air in a new build. You have to feed the engine.
Before we hand over the keys to the customer, how do we verify our work? The smoke test.
This is the old school way, but it works. You block off the top of the chimney, put a wet board or a piece of stone over it. Then you build a small smoky fire in the firebox.
What do you use for that?
Damp straw is traditional, or a bit of tar paper, something that smolders and makes thick, oily smoke.
So you fill the system with smoke.
You create positive pressure inside the chimney because the top is blocked. Then you walk around the house with a flashlight. You look at the masonry joints in the attic, the second floor, the basement.
And if you see smoke...
If you see wisps of smoke coming out of the mortar joints, you have a leaker.
And a leak is a fire hazard.
A leak means hot gas can get out. It means carbon monoxide can get out. You have to find it and fix it. Grind it out and repoint it before you unblock the top.
Better to find it than have the customer smell smoke in the baby's bedroom upstairs 3 months later.
Absolutely. That is a callback you never want to get.
All right, we are closing in on the hour. We've covered the history of Count Rumford, the physics of the throat, the chemistry of the mortar, and the code. But we can't leave the apprentices without the pro tip from the scaffolding.
The grand finale.
This one is about the fire brick layout. The scenario. You have mixed your refractory water, you have your soup, you're ready to go. You start laying your first course of fire brick on the floor of the firebox. You are working your way across the back wall.
I can see it happening. I can feel the panic setting in.
You get to the last brick, and you have a gap. But it's not a brick-sized gap. It's 1/4 of an inch, or maybe 3/8.
A sliver. A useless, impossible sliver.
Have you ever tried to cut a 1/4-inch sliver off a fire brick with a wet saw?
It is a nightmare. The brick crumbles, it explodes, the blade binds, or you cut your finger. It's impossible to get a clean cut.
So what do guys usually do? They panic. They fill that gap with a big glob of mortar.
Which looks terrible. It looks unprofessional. It stands out like a sore thumb, and it will crack. It's a failure point.
It screams, I didn't plan ahead.
Exactly.
So the pro tip.
Dry lay the first course.
Before you mix the mud.
Before you even open the bag. Before you get water in the bucket. Take your fire bricks and lay them out dry on the hearth. Place them exactly where you want them. Use a little spacer, a piece of cardboard or a tile spacer, to mimic the 2mm joint.
And if you get to the back and you have that awkward 14-inch gap.
You don't cut a sliver, you fix it in the bond. You open up the joints between the other bricks, just a hair, a 1/2 millimeter here, 1/2 millimeter there. You spread that 14-inch discrepancy over 10 bricks.
And suddenly you end with a full brick.
Or a solid half cut. But you never, ever end with a sliver. You cheat the bond dry. You mark your lines with a pencil on the concrete hearth. Then you mix the mortar.
Fighting for space at the back of a firebox is a mistake you only make once. It's panic mode. The mortar is drying, the boss is watching, and you are trying to cut a slice of toast out of a rock.
And you can't erase mortar. Once it's down, it's down. Dry laying takes 5 minutes. It saves you an hour of misery and gives you a product you are proud to sign your name to.
That is the difference between a stacker and a mason. A stacker just puts things on top of things. A mason plans the bond.
It really is. It's forethought.
Well, there you have it. Fireplaces, they are the heart of the home. But they are also a complex machine made of stone and clay.
Masonry is permanent. A bad fireplace stands for 100 years, aggravating every owner who tries to light it. Or until it burns the house down. Don't be that guy.
Make it draw, make it safe, make it last.
Keep your levels true and your joints full.
This is the Canadian Masonry Podcast. We'll see you on the next deep dive.